For my project, I wanted to look at how high water would rise above a vertical overflow pipe. During my internship, I was tasked with working out how high the water would rise above the overflow pipe in a finger pond in order to verify that we wouldn't overflow the finger pond. My assumption was that water would behave similarly to that of a sharp-crested rectangular weir with a width the same as the circumference of the pipe plus a bit more to account for the curvature. Using Fluent, I can get a better estimate. These slides show the math I am using. Method 1 is developed from Bernoulli's principle. The Francis equation was also developed from Bernoulli's, but it is specific to imperial units. The picture shows an overflow pipe for a dam, but the principle is similar except for this: I am simulating a 4-inch Schedule 40 sharp-edged pipe. To perform the simulation, I am using a model created in SolidWorks and then modeled using Fluent. The SolidWorks model is very simple and needed to be built using a negative model of what I wanted. I experimented with a different setup where it used an inlet pipe, but there was too much turbulence. This image shows the workbench setup I used initially, hoping I could set it up parametrically, but ANSYS was slower to calculate that than in Fluent itself, and the model would take forever to load. Overall, I think it became 40 gigabytes or so worth of simulation. This is what my final simulation looked like. I used a double precision explicit volume of fluid model with an open channel flow flag and a realizable K-epsilon model of viscosity. Results. Most of the results are presented as animations of the contour of the air volume fraction, where red is air and blue is water. Starting with 50 gallons per minute, the flow goes over nicely. Next, I use the volumetric render to display some more detail about the flow within the pipe. Now you will see from 100 gallons per minute to 200 gallons per minute. You will notice that the height above the pipe increases. You will also notice the weird pulsing, which I find pretty cool. Lastly, these are a few more animations, but I don't trust the results, yet they offer good visualization. Particularly, there are two animations where the left inner wall of the overflow pipe seems to hold a bubble of air. I think this could be from a bad mesh. Finally, these are the numerical results. The first graph shows the height of the water versus time. You will notice that 250, 275, and 300 gallons per minute plots are significantly different. With this data, I used MATLAB to perform a curve fit and compare against the Francis equation. I got a similar curve fit of the form shown in the following slide. However, you will notice that there is some error. I could probably achieve greater accuracy by creating a better mesh at the expense of computation time. I could also decrease the time step size while increasing the computation time further. The current model took roughly 3 hours on a 16-core server. If I had more time, I could have set it up to run parametrically and achieved more data points, assuming the bug I found wasn't an issue. Lastly, to confirm the hypothesis, it would be cool to verify and would not be difficult to set up the model in a lab.